Hello, and welcome to the first video of Thermodynamics. Now, thermodynamics is a very interesting subject. It is inherently tied with what else is called statistical mechanics, which will be covered also later. But for now, we're going to learn some thermal physics, basically, so transmissions of heat energy. Now, the first thing we need to introduce is the idea of temperature. What is temperature? And I'm just going to call it capital T. Well, temperature isn't like super strictly defined right now, but what we can say is it's some sort of measurement of energy. So it's a measurement of energy in a system. Now, what a system is can depend a lot. Like the system could be the piece of paper right here, it could be the desk, it could be two fluids interacting with each other, anything really. And you can always measure the temperature of that system. Now, when two systems interact with each other, they behave differently. And the interactions going on between them won't be covered right now, but eventually those interactions will end and reach what's called equilibrium. Now this equilibrium is basically when the temperature of one object equals the temperature of the second object. Like right now, the temperature of this paper should be the same as the temperature of this desk, because these two objects are in contact with each other, and so they should be in an equilibrium temp state right now, so the temperature between them is the same. Now, some objects reach that faster than others, and we'll learn more about that in a little bit. But right now, we need to go to the temperature scales. So the first temperature scale is going to be the Celsius scale. This scale is very useful for like everyday life. Water freezes at 0 degrees Celsius, and water boils at 100 degrees Celsius. So, as you can see, this is very great for everyday life. We live in between like these temperatures. These are two extreme temperatures, but we live around like 30 degrees Celsius. So this is around where we live. Now, the next temperature scale that's pretty useful for scientists is going to be the Kelvin scale. Now, the Kelvin scale is very similar to the Celsius scale, except for the Kelvin scale 0 point is going to be absolute 0. Where this 0 degrees Kelvin means 0 energy. So like we said before, how T is a measurement, temperature is a measurement of energy, absolute 0 is 0 energy at all. Whereas in Celsius, 0 degrees Celsius is freezing point, but there's still energy inside of the ice. Here, there's no energy at all. It's completely heat death of the universe, basically. Now, next point is going to be 273 Kelvin, which is a lot, right? Degrees Kelvin. That is our new freezing point. And by freezing, I mean freezing of water into ice. So 273 Kelvin is freezing. And so now I'm just going to write the simple equation where Celsius equals Kelvin plus 273. Oh no, I got that backwards. Kelvin equals Celsius plus 273. That's what it is. So, this equation, it's very useful to convert between the two. We will mostly be using Kelvin when studying thermal physics, though. It's more useful than Celsius because we're not always just working with water, and Celsius is really only convenient when we're working with water temperatures. All right. And also Kelvin is known as, since this is absolute zero, Kelvin is the absolute scale. So this temperature, no matter what, it's just always the same. All right, and then the last thing I want to show off today is going to be what's called the ideal gas. Now, the ideal gas is very interesting. It's one of the most important things we might learn in this class. And so I'm just going to give you the equation. PV equals N R T. T is in temperature. R is a constant. N equals number of moles. You can, if you know chemistry, it's the same moles as in chemistry, related to Avogadro's number, where the number of molecules equals N times Avogadro's number. And Avogadro's number is 6.02 times 10 to the 23. An important number. V is going to be the volume of the gas. So really, this might be the first this is the first property of actual gas that we know of. Because as you know, gases can change volume based on whatever container they're in. So they fill the entire volume of their container, unlike solids and liquids. And then we have pressure for P. P equals pressure. Now classically, we remember pressure as force divided by area. And it's the same here. Basically, this pressure comes from the particles hitting the sides of the container. So we have a box of volume V with some particles in it. N number of particles. Either N or N, whichever N you like, at a certain temperature. So these particles are at a certain temperature, and now they fill this fixed volume V, and then they hit the sides of the box. The particles are moving around. They don't sit still. And basically, every time the particle hits the side of the box, that is what's measured by the pressure. So the pressure is just measuring how much the gas is pushing outside of it. And as you can see from this equation, if you increase the temperature and keep everything else constant, because this is a constant, the number of particles is going to be constant, the volume is going to be constant because it's still in this box, that means the pressure has to increase. So the particles are going to be hitting the side of the container even harder. So this is just a basic idea of the ideal gas. We will do a lot more with the ideal gas later, and I will show you even more of thermodynamics. But for now, I will say goodbye. Thank you.